Hello friends, in today's video we're going to be doing a quick introduction to limits, including how to compute them using tables and graphs. But before we get into that, let's first dive into why we need limits in the first place. So let's suppose that we're at the top of a building and we drop a ball from the top of the building and we want to figure out how fast the ball is going after, let's say, 2 seconds. So we want to know how fast this ball is going, or the speed, or maybe the velocity of the ball. And you might remember from college algebra that velocity is measured as distance divided by time, which makes sense if you think about the units. The units on velocity is typically something like miles per hour, which is a distance divided by a time. Now in reality, the formula that you're actually using back in college algebra is that velocity is equal to the change in distance over the change in time. And we can denote that as a delta d over delta t. Now there's something seriously wrong with this formula when we're trying to figure out what the velocity is at a given time. So at the time t is equal to 2, well, how far does it travel at a given time? Well, at a time it doesn't travel anywhere, and there's no change in time, so we end up with this formula being 0 over 0, which is undefined. Alright, so this formula doesn't work for at a given time, but it works on intervals. So maybe we figure out how fast it's going over the entire interval 0 to 2 seconds. Now, if we did compute this, we would find that the average velocity on this time frame is approximately negative 32 feet per second, where the negative is there because the object is going downwards. Now, the problem with this is that objects, when you drop them, start going faster and faster. And this is an average over those first 2 seconds. So at 2 seconds, it's actually going faster than 32 feet per second. All right, so what can we do to improve this? Well, 2 seconds is a long time for an object to be dropping. It speeds up quite a bit. So rather than doing 2 seconds, how about we do just the last second that's dropping? And if we do that, then the average velocity on this time frame is negative 48 feet per second. And this will be a little bit closer to the actual answer. Well, why stop there? Why not just go down to a tenth of a second? And if we went down to a tenth of a second, the last tenth of a second that's dropping, we're going to get an answer about negative 62.4 feet per second. And if we took it even further, down to say a thousandth of a second, we would get it to be negative 63.984 feet per second. And what we can see from these values is that the velocity is getting closer and closer to negative 64 feet per second. And that's really the idea of the limit, is that we can never go all the way to 0 time frame, because then you're doing 0 divided by 0, and that's not allowed. But we can get closer and closer and closer to a time frame of 0, and we can see what this value is going towards. So in this way, we would say that the limit of the velocities is going to negative 64 feet per second. Now, maybe you agree that this is going to negative 64, but maybe you look at this number, negative 63.984, and you say, that's not really that close to negative 64. I need it to be a little bit closer. And in reality, the idea of a limit is I can get as close as I need to, or as I want to negative 64 to say that the limit exists. So maybe you need it to be negative 63.9999 before you're satisfied. Well, I can make it that close to negative 64 simply by taking a smaller time frame. So I could take the average velocity, let's say on a millionth of a second, then I would get negative 63.999, and then we get an 84 at the end here, and maybe that satisfies you, okay? But maybe if it doesn't, you say, no, I need like 7 nines there before I'm satisfied. Well, I simply just take a smaller and smaller time frame, and that's the idea of the limit there, is that I can make it as close to negative 64 as you need it to be simply by making that time frame smaller and smaller and smaller. All right, so let's formalize this in a problem you might see in your homework or maybe a test or something like that. So here we have a drone flying so that its position in meters after t seconds is given by the formula s of t is equal to t squared plus 2t, and we want to find this instantaneous velocity at time is equal to 3. So what I want to do here is find the average velocity on time frames around time is equal to 3, okay, maybe a 1 second time frame, and then allow those time frames to get smaller and smaller. So instead of from time is equal to 2 to time is equal to 3, then maybe I'll do from like 2.9 to 3. And what I'm going to do is just see what is the tendency of these numbers as I make the time frame smaller and smaller. All right, so again, velocity is given by a change in distance over a change in time. And how are we measuring distance in this? Well, it's the position of this drone. And we have this formula for it. We can figure out what the position is at a given time simply by plugging that time in. So S of 2, for example, where it is at after 2 seconds is 2 squared plus 2 times 2, or 8. And S of 3, where it is after 3 seconds, is 3 squared plus 2 times 3, or 15. So the change in distance here is S of 3 minus S of 2, or 15 minus 8. And the change in time is 3 minus 2, or 1. So overall, we get a velocity here of 15 minus 8, or 7, over 1, or just 7. And the units on this is the distance is measured in meters, and the time is measured in seconds, so meters per second. Now, on its own, this number 7 meters per second really doesn't tell us anything. What we need to do is continue this process for smaller and smaller time frames. So now I need to figure out where it is at 2.9 seconds. So again, I would just plug in 2.9 squared plus 2 times 2.9. And if we do that, we'll get 14.21. All right, so the velocity on this time frame, again, is S of 3 minus S of 2.9, the change in position, or the distance you travel, divided by the change in time, so 3 minus 2.9. And if we do this computation, we'll get the answer to be 7.9 meters per second. All right, and still these two values don't tell me very much. What I need is a bunch of values. So I just need to repeat this process on smaller and smaller time frames. So we basically do the same exact computation, just allowing this time to get closer and closer to 3. So now 2.999 to 3 seconds. And if we do this, we're going to get the velocity to be 7.999 meters per second. Okay, and now I'm getting a better feel of what's happening to these velocities. As I'm getting a smaller and smaller time frame, it looks like this velocity is getting closer and closer to 8. Now, even though I think that these values are going to 8, I still want to check another value. And in particular, one thing that I haven't done yet, that is important when you're doing these, is that you should usually approach limits from both sides. That is, we've been taking time frames below 3 from 2 to 3 seconds, but we should also take time frames from 3 to 3, let's say 0.0001 seconds. We should take small time frames on the other side of 3 just to make sure that this object is going towards 8 on both sides. Okay, and if we do this, the same idea, we're going to do S of 3.0001. Again, we calculate that by just plugging in that number into our function, minus S of 3, all over 3.0001 minus 3. Same exact formula. We do all this computation, we're very careful in our calculator, and we'll get this velocity to be 8.0001 meters per second. So in this way, we can see that our velocity is going towards 8 no matter which side we approach that time frame of 3 from. And that is an important concept for limits, which we'll get into in later examples. All right, let's take a look at another major example with limits, and that is to find the slope of a curve at a given point. Now, here we have the curve y is equal to x squared, and you might say, well, that doesn't have a slope, it's not a line, and only lines have slopes. Okay? But if you look at a curve, or at least most curves, and you zoom in really closely, it will look like a line. And you're sitting on an example of that right now, the Earth. The Earth is curved, but we're so close to it, it looks flat. Okay? So that's the same thing will happen with curves like a parabola. If you zoom in really, really close, say at x is equal to 2, it will take on the shape of a line, and that line we're going to call later on in calculus the tangent line. And in reality, that's what we're after. We're trying to find the slope of this tangent line. So let's just start there with the slope of a tangent line. Well, the slope of a line is just rise over run. And of course, rise is a difference in y coordinates, and run is a difference in x coordinates. All right, and we're going to run into that same exact problem if we try to find the slope at a point, say at x is equal to 2, and we don't allow x to change. We're going to get 0 on the bottom and 0 on the top, and again, that's undefined. All right, so what we really need to do is join two separate points together, say 2 and x, and then very similar to what we did before, we'll let x be, say, 3, and then we'll let it get closer and closer to 2. So what does this look like algebraically? Well, we're trying to, again, figure out this slope, and we're joining these 2 points, x and 2. So our run is just going to be x minus 2. Now, what about our rise? Well, if we know what x is, we can figure out what our y is by using the formula. Well, if x is x, then y is equal to x squared. And if x is 2, then y is equal to 2 squared. So we end up with x squared minus 2 squared for our rise. So this is the general formula for finding the slope of any point x and joining it to the point 2 on this parabola. And now what we want to do is, again, let x get closer and closer to 2. And the way that we write that in calculus is with the following notation. We're going to write LIM, which stands for limit, and then an x arrow 2. And what that means is we're going to let x get closer and closer to 2 and see what happens to this function behind it. Now later on in calculus, you'll figure out other ways to do this limits, but for now I'm going to do this with a table. So what I'm going to do is just make a little table here, and I'm going to pick values of x that are closer and closer to 2 and plug them into this slope. X squared minus 2 squared is x squared minus 4 over x minus 2. And I'm just going to see, do these values go to anything in particular? All right, so I'm going to start with a number that's relatively close to 2 but easy to compute. Let's say x is equal to 1. Okay, and I'm going to plug it in. So 1 squared minus 4 over 1 minus 2. And we're just careful with this arithmetic, and when we do this, we're going to get 3. Okay, and again, a single value really doesn't tell you anything. I need to continue and allow x to get closer and closer to 2. So now maybe I'll plug in 1.9. Now if I plug in 1.9, I'll get 1.9 squared minus 4 over 1.9 minus 2, and I'll get 3.9. Okay, now I'll try again, 1.999, and if I do that, I'd get 3.999. Okay, now it looks like these values are getting closer and closer to 4. And again, I can make it as close to 4 as I like simply by just adding more 9s over here on the x. Now in reality, we've only done half the problem, because remember that we have to approach our limits from both sides. So I also need to take values of x that are close to 2 but are bigger than 2. So for example, I need to plug, say, 3 into this function x squared minus 4 over x minus 2. And if I do that, I'd get 3 squared minus 4 is 5 over 3 minus 2 is 1, so we'd end up with 5 for our slope here. And you say, well, that's not very close to 4, but remember, we're supposed to be getting closer and closer to 2. So now I'm going to take something like 2.1. And if I take 2.1, I plug it into that function, I'm going to get 4.1. And if I take 2.01, I'll get 4.01. And again, you'll see that these values are getting closer and closer to 4 on both sides. So overall, we would say that this limit is equal to 4. Again, we can make it as close to 4 as we like on both sides of 2 simply by making that x value closer and closer to 2. All right, let's take a look at an example of just finding a limit not attached to any bigger problem. So here we have the limit as x goes to -2 of x cubed plus 8 over x plus 2. And again, the idea of a limit is that we're going to take x values that are closer and closer to -2, and we're going to plug it into this function x cubed plus 8 over x plus 2. And we're going to see if those values tend towards anything. So again, I'm going to take a value close to -2, let's say -3, okay? And we're going to plug it into this function, -3 cubed plus 8 over -3 plus 2. Now, if you're doing this in a calculator, just be careful that you actually have fractions open or use parentheses around the entire top and bottom when you're doing this arithmetic. And if we do this, we'll end up with an answer of 19. Okay. Now, -3 is close to -2, but it's still 1 unit away. So let's get a little bit closer. let's say that we plug in negative 2.1. So now if we plug in negative 2.1, okay, again, all we're doing here is negative 2.1 cubed plus 8 over negative 2.1 plus 2. Okay, and again, we can do that on the front screen of your calculator. I'm actually doing this on my calculator on the grapher, and I'm using the trace key. I basically just typed in this function into the grapher, and I just trace a bunch of different x values, and that's usually good enough. So we'll get 12.61 if we do this computation. All right, so let's get a little bit closer to negative 2. Let's say negative 2.01. And if we plug that in, again, we plug it into our function just like before, we'll get 12.0601. Okay, we can see that these values are getting closer and closer to 12, but just for good measure, let's do one more. I usually ask my students to do at least 4 on each side. So negative 2.001, we plug that in, we'll get 12.006001. And again, it looks like these values are getting closer and closer to 12. Now, in reality, all we've computed here, again, is just what we call a one-sided limit. And the notation for this one-sided limit is the limit as x goes to negative 2. And we put a little minus sign here, and that means from the left. All these numbers of x are on the left of negative 2 on the number line. And if we do this, we've computed that this limit is equal to 12. So now what we need to do is we need to do the limit as x goes to negative 2 from the right side. Same exact function, x cubed plus 8 over x plus 2. And again, we need to make sure that this goes to the same exact value. Well, how do we do this right-sided limit? Well, we do it the same as the left-sided limit with a table. So we're going to take x's, we're going to plug it into our function, x cubed plus 8 over x plus 2. But this time we're going to take numbers to the right of negative 2 on the number line. So numbers like negative 1, negative 1.9, negative 1.999. And we're doing the same exact thing as we did before. We're just plugging into the function x cubed plus 8 over x plus 2, and we're computing it and seeing what we get. When we plug in negative 1, we're going to get 7. When we plug in negative 1.9, we're going to get 11.41. And when we plug in negative 1.999, we're going to get 11.994001. And again, we can see that these values, as we go farther and further down the table or closer and closer to negative 2, these are all going towards 12, just the same. Okay? And in fact, you're going to learn a property of limits later in calculus that says that the limit only exists if these two one-sided limits go to the same value, which they do. They both go to 12. So that means that our overall answer is 12. All right, let's take a look at another example, finding limits with tables. This time we're just going to do a one-sided limit. So we're going to do the limit as x goes to 0 from the right. Again, that little plus sign means from the right. And of cosine of pi over x. So again, all we're going to do is make a table where we're going to pick x values that are closer and closer to 0, but they have to be to the right of 0 or bigger than 0. So again, I'm going to start with a number relatively close that's easy to plug in. Let's say 1. So we're going to get cosine of pi over x. We're just going to plug in 1, so cosine of pi over 1. And we can use our calculator, but make sure when you're doing your calculator in calculus to always set it to radians. Okay? And when we do this, cosine of pi is just going to be equal to negative 1. Now again, a single value doesn't really tell you anything on these limit tables, so we just need to continue. So if we plug in 0.1, we'll get cosine of pi over 0.1. And this time we're going to get positive 1. Okay, so let's go a little bit closer and see what happens. 0.01, and we get cosine of pi over 0.01. And we're going to get positive 1 again. And maybe if you plugged in 1,000th, you're going to get positive 1 again. And you're going to be pretty convinced that the answer is just 1, because these values are not only getting close to 1, they are just 1 every single time. But we actually made a little mistake here, which we haven't run into yet. And that is because cosine is periodic, we're just hitting these peaks of cosine. So when you're making one of these tables, most of the time it's okay to end your digits with 1s or always end them with 0.99s, things like that. But for trig functions, you typically want to vary this last digit. And if we do that, we get a little bit closer. So, but this time we change that last digit to say a 3. So now we plug in 0.0003, and now we're going to get negative a half. Okay, and now if we get a little bit closer, okay, let's say 0.00007, okay, and now we are at 0.623, okay. So now it doesn't look like the values are going to anything in particular, and in fact they aren't. Okay, these values are just climbing up and down around cosine between -1 and 1, and they're never approaching a single value. So these don't approach any single value, and when that happens, we say that this limit does not exist because it doesn't go to anything in particular. Okay, and we typically abbreviate that as DNE. So there's two major lessons in this example. Number one, when you're using your calculator in calculus class, make sure you set it to radians. And number two, whenever you're dealing with a periodic function like a trig function, when you're making these tables, don't always end in the same digit like 0.1 or 0.9 or something like that. Vary the last decimal digit here, okay? Otherwise, you might run into answers that aren't correct. All right, now let's take a look at limits using graphs. So here we have a graph, and we're going to find the limit as x goes to 3 from the left, then from the right, and then overall. So we'll start with this first one, the limit as x goes to 3 from the left. And all I want to do is basically jump on my graph, not at 3, but to the left of 3. And then I want to follow that graph and see, does the y value go towards any particular value as x gets closer and closer to 3? So as x gets closer and closer to 3, you can see that I'm going to this little open circle. Now, I actually never reached that open circle, but that's okay. I'm getting closer and closer to it, and all we need to do is figure out where is that open circle. Well, it's at the value y is equal to -1. So in this way, this limit is equal to -1. Now, what about from the right side? Well, it's the same idea, but this time I want to go to the right of 3. So go over here to the right of 3. Hop on your graph, and then follow that graph back towards x is equal to 3 and see, does it go to any particular value? And we can see that again, it's going towards that same y value, y is equal to -1. So both the left and the right limits are going to -1, and when that happens, your overall limit, yellow and blue make green, also goes to -1. All right, let's take a look at the same graph. This time we're going to do the limit as x goes to 1. We're going to start off from the left. So again, we're going to go to 1 on the graph, go to the left of it, and then hop onto your graph, okay? And then figure out what happens as x goes towards 1. As we start to move towards x is equal to 1, are we going to any particular y value? And you can see that we're going to this y value right here, which looks like it's halfway between 4 and 3. So I'm going to say it's 3.5 or 3.5. Okay. Now let's try it from the right side. So again, we're going to go to the right of 1 on our number line. We're going to jump up onto our graph. Okay, and we're going to follow that graph as x gets closer and closer to 1. And as we do that, we can see we're going to this open circle, which is at the y value of 1. Okay. Now, for the overall limit from both sides, well, one side goes to 3, and the other side goes to 1. So overall, they don't approach a single value, and when that happens, we say that the limit does not exist. All right, let's try one more with this graph. So again, we're going to do the limit as x goes to -2 from the left to start. Again, we're going to go to -2 on the x-axis. We're going to go a little bit to the left. We're going to hop up onto our graph. Maybe you can picture yourself walking on the graph. And where are you going to walk towards? Well, you're going to walk towards this open hole. You're never going to reach it, but you are walking towards that y value. And again, that y value is 2. Okay. Now, what about from the right? Again, you're going to go to x is equal to -2 on the x value. You're going to go a little bit to the right of it. You're going to jump up onto this graph. Again, you can kind of picture yourself up here walking on this line, and you're going to walk towards x is equal to -2, and you're walking towards that same exact hole in the graph, so you're walking towards 2. Okay. Now overall, both sides, you're walking towards that same place, so your overall answer is 2. All right, so one thing to note here is that you don't actually want to go exactly to -2. If you looked at exactly -2 and you plug that into your function, okay, you would get that that value is equal to 1. Okay, but that's not what a limit says. A limit never actually goes exactly to that point. It just gets closer and closer. So again, when you do these limits, you want to get close to -2 and then move in one or the other direction and then see what happens as you tend back towards the point. And as always, please take a moment to like this video and subscribe to my channel.